All right, today we're gonna crack a code. I mean a code that basically runs everything you see move in the entire universe. Yeah, we're talking about the secret of motion itself.
You know the feeling, right? You're trying to shove some heavy piece of furniture across the room, or maybe you're just hitting the gas in your car. You feel the push, you see things start to move, but what is actually going on under the hood, physically speaking? It turns out there's this one beautifully simple key that unlocks the whole thing.
So in physics, we usually start by just describing motion. That's called kinematics. We talk about how fast something's going, where it is it speeding up, but that's just telling the what. The really interesting part, the part we're digging into, is the why. That's dynamics. And dynamics is all about the forces that make things move in the first place.
Think about that box again. When you push it, it's not just you and the box. Oh no, it's this whole invisible battle going on. There's the force from your hands, yeah, but there's also gravity pulling it down, the floor pushing right back up, and that pesky friction trying to stop you. To make any sense of it, we need a way to map out this invisible world of pushes and pulls. And the key to translating all this chaos, the absolute cornerstone of what we call classical mechanics, is Newton's second law. Seriously, this little equation is so powerful, it's like the Rosetta Stone for understanding why things move.
And there it is, F equals ma. Just 3 letters, but man, they literally changed the world. It looks almost too simple, right? But the real magic is what each of these letters actually stands for. So let's break them down.
Okay, first up, F is for force. This is our why. It's any push or any pull that can make something change its motion. The way to think about it is, if there's no net push or pull on something, its motion is just going to stay the same. It's that simple. And we measure these pushes and pulls in a unit called newtons.
Next, we've got M for mass. Now, be careful, mass is not the same as weight. Mass is really a measure of an object's inertia. You can think of it as its stubbornness, how much it resists being sped up or slowed down. The more stuff something has, the more mass it has, and the more force you're going to need to get it to change what it's doing. And finally, A for acceleration. This is the payoff. This is the result. It's the change in velocity that you get when you apply that net force to that mass. And just a quick reminder, acceleration isn't just about speeding up. Slamming on the brakes is acceleration. Taking a sharp turn is acceleration. Any change in velocity counts.
So, what kind of forces are we usually talking about? What gets to be the F in our equation? Well, in our day-to-day world, it's usually the same cast of characters. You've got gravity, that constant downward pull. Then there's what physicists call the normal force, which is just a fancy way of saying a surface, like a table or the floor, is pushing back, so stuff doesn't fall through it. You've also got tension if there's a rope or a cable, the good old drag of friction, and of course, the force from a spring. Now, friction is a really cool one because it's kind of got 2 personalities. First, there's static friction. That's the sticking force. It's like this little guard that pushes back against you, and it can actually push harder and harder, but only up to a certain point. That's why its formula has that less than or equal to symbol. Once you push hard enough to overcome it, bam! It switches to kinetic friction, which is a constant force that just resists the sliding motion. And see how its formula is a simple equal sign? That tiny difference in the math is huge in the real world. Okay, with all these different forces flying around, things can get messy fast. So how do we keep it all straight? Well, physicists have this brilliantly simple but incredibly powerful tool. It's called a free body diagram. And let me tell you, this is probably the single most important step to solving almost any problem involving forces. And the process is super straightforward. First, you just pick one object you care about and mentally put it in a bubble, ignoring everything else. Step 2, you identify every single outside force that is touching or acting on that one object. Gravity, pushes, friction, all of it. And finally, you draw those forces as arrows. We call them vectors, all starting from the center of the object and pointing out. And just like that, you have a perfect map of the situation.
All right, let's put this new superpower to the test. Here's a classic setup. You're pushing a block, M1, which then pushes another block, M2. Let's say it's on a frictionless table, just to keep things simple. They both start moving together, but stop and think for a second. From the point of view of that second block, M2, you're not even touching it. So what force is actually making it accelerate forward?
And this is where the free body diagram just cuts right through the confusion. Look at the diagram for M2. See? Your hand isn't there. The only thing pushing it forward is the contact force, that normal force from block M1. It's like a little chain reaction, and the diagram forces you to see that M2 only cares about the forces touching it directly.
Okay, so we've seen how this works for a couple of blocks on a table. But here's the truly mind-blowing thing about F equals ma. It's not just for little lab experiments. This one simple law scales up to describe just a staggering range of things all across the universe.
I mean, really think about it. A car accelerating away from a stoplight? That's F equals ma. The friction that grips the road and lets that same car turn a corner without sliding off into a ditch? That's F equals ma. A satellite whipping around the Earth in a perfect orbit, held in place by gravity? You guessed it. Also F equals ma. The bounce of a spring. It's the same fundamental rule over and over and over again. This actually brings us to a really common point of confusion in physics, centripetal force. It sounds like some new, special kind of force, doesn't it? But it's not. The word centripetal is just a job description for a force. It's not a name, it's a role. All it means is center-seeking.
So when that car is turning the corner, the force of friction is playing the role of the centripetal force. It's the one pointing toward the center of the turn. When a satellite is orbiting the Earth, gravity is playing the role of the centripetal force. So don't think of it as a new force. Just think of it as a label for whatever force is doing the job of pulling something into a circular path.
And now for what might be the most important pro tip in this whole explainer. This is something that trips up so many students, so listen close. Get this burned into your brain. Friction is not a force. Here's what that really means. F equals ma is a cause and effect equation. The F side, the sum of all the real pushes and pulls, that's the cause. And the ma side, the resulting acceleration of the mass, that is the effect. They are equal, for sure, but they are not the same thing. One causes the other.
So here's the takeaway, the thing you have to remember. When you're drawing that all-important free body diagram, that map of all the real forces, you never, and I mean never, draw an extra arrow and label it ma. Why? Because that's like adding the effect back into the cause side of the equation. You'd be double counting, and all your answers would come out wrong. Look, F equals ma is just one of the most successful ideas in the history of science. It really is. It explains everything from an apple falling from a tree to the waltz of the planets. It gives us this incredible feeling that the universe is orderly and understandable. But it also makes you wonder, right? If this one simple rule explains our visible world so darn well, what are the rules for the worlds where it doesn't work? The worlds of the incredibly fast, like in relativity, or the incredibly tiny in quantum mechanics. Now that is a story for another time.